we're going to start in now, on C13. All right, so we'll just do a little bit of intro, and that's about mostly what we'll do today. Okay? All right, so this was just our beginning slide. Let's see here, switch to second screen. I don't know, I thought one of the, oh yeah, I tried this before. I know, I've done it before with the second screen, and then it didn't show that other stuff, so it doesn't get blocked by some of that other stuff. But, all right, go away. All right, so this is what we started out before. We know that we can detect nuclei, and they give us information about the number and the adjacent atoms and the environment and all this kind of stuff. Okay, so here is an example of a C13 spectrum. This is cholesterol. So let's just look at this and pick out some things that might be similar to what we've been learning in proton NMR and what might be different.
Different. There's no coupling.
All right, no coupling. Yeah, we have a much broader, bigger chemical shift. So let's see, this is all singlets. Okay, chemical shift. Instead of 1 to 12 or something, it's 1. This is a short one. This would be something from 0 to maybe 220.
Similar, you still have a solvent peak.
We do have a solvent peak. Okay, I'll fill in a few things here. Similar, I would say, is that even though the chemical shift range is much greater, the chemical shifts do kind of follow a similar trend. In that, for example, on this molecule, these downfield carbons would be for the double bond, right? sp2, we know if we have a proton NMR, the double bond protons are downfield. And the next most downfield one would be for the carbon that where the oxygen is, right? So it's kind of in the middle, just like if we look at a proton on a carbon next to an oxygen, okay? Some other differences, one other difference that I'll put here is that it turns out, it's hard to tell in this case, but that the peak areas, area under the curve, are not proportional to the number of carbons. So in general, in C13 NMR, we cannot integrate the peaks to determine the number of carbons.
It doesn't give us any piece of information.
Well, I think what we can do is if we know that we have carbons of similar type, hybridization, or the number of protons that are attached, we might be able to get a rough estimate of 1 to 2 or something like that. It's not that we cannot integrate the signals, it's that we don't run the experiments in a way that allows us to integrate the signals. We can run the experiment in a way to allow us to integrate the signals, but it takes a much longer time. So we don't usually do that. Okay, so we'll talk about that as we, talk about some of these experiments. All right. Oh yeah, we already talked about, here's in chloroform. This is the solvent. right? 77.0, 3 peaks like this, and we just talked about why we have 3 peaks, right? It's because it's coupling to the deuterium.
Oh. So you still use deuterated or solvents?
Yes. We still need deuterium. In the NMR, the signal for the NMR, locks as a reference signal onto the deuterium. And that's how it compares one's, frequency to another frequency. But so like Steve was doing, he was using a small amount of deuterium with a larger amount of protonated solvent. So he needs enough deuterium in there to lock the signal on there so it doesn't wander during the experimental time. But, and you could do something like that here as well. Or you can actually have these tubes that have a small inner tube, and you could have some deuterated solvent in there too, and not in your actual sample. Okay, so a little bit of theory. So signals are generated just the same way. So our pulse sequence is essentially the same. That we'll add in something different that allows us. We notice that all those peaks were essentially singlets. But again, that's not because there's no coupling. It's because we run the experiment in a specific way to give us singlets. All right, so C13 is much less sensitive than proton NMR because it has a low natural abundance of C13. And we talked about before, too, this magnetogyric ratio, this gamma, when we looked at this equation. I think maybe we mentioned that there was a big difference. So here's actual values for the magnetogyric ratios for proton. It's in whatever units here, radians per second per Tesla, whatever. It's roughly a 4-to-1 ratio. Okay. So that means that the energy gap for protons is 4 times as big for a given magnetic field, right? And that means that that Boltzmann distribution, the amount of excess protons in the plus spin is bigger for proton than it is for carbon, right? Because the bigger the energy gap, the more of the excess spins we have. There's more in the lower energy state. Okay. All right, so we have lower delta E, less net magnetization. All right, so all peaks as singlets. So we should see these carbons coupled by the protons, right? But what we do is we do similar to what we did in that selective decoupling, but we do a broadband decoupling. So we decouple all the protons, so it removes the coupling from the protons to the carbons. Okay? So no coupling because of our experimental setup. We run the experiment specifically to do it this way. So for example, here are 2 spectra. The bottom one, this is the decoupled. It's like the one we just saw. So, well, it's hard to tell actually down in here that they're necessarily all singlets because there's a lot of peaks in there. But all of these peaks are singlets, And up here is actually the coupled spectrum. Okay, so notice some of them like here. So this is for the CH, that's for this carbon right here that has an H on it. And in the coupled spectrum, notice that it's a doublet, right? Because it has one proton attached. So N plus 1 splits it into a doublet. Okay. Oops. This one over here is just a singlet. Right? And it's still a singlet, and that is this carbon here. Right? It has no protons attached. Okay? If we look down through here, we could just pick out some of these other ones. We talked about already that this carbon here is the one where the alcohol is attached. Notice if we look up here, this one's a doublet because this carbon has one proton attached. Okay? The other one that's easy to, well, there's a few that are easy to pick out, but like this one down here, it's a quartet, right? And so that is for one, I think it's this one here, for one of the methyl groups, right? 3 protons attached, N plus 1 gives it a quartet. So this is a quartet. I was just looking through here. It looks like to me that maybe this one right here might be a triplet. You know, and again, it gets decoupled to a singlet. All right, so the coupled spectrum, what it essentially, the coupling that we see most easily is the one bond coupling. Okay, so this is J1. So it shows how many protons are attached.
Does it do any, I always forget the word, the symmetry, but not because of the magnetism?
Oh, that magnetic non-equivalence.
There we go.
I don't know if we could set up a situation like that with just one bond coupling.
Okay.
Yeah. You know, and there may be longer range couplings that are in here, but they're much, much, much smaller than this, so we don't really see that. Oh, we're past time anyway. All right, so sometimes what you'll see on different spectra, even though they're decoupled spectra, we will see things like singlet, doublet, 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 quartet. And what those mean is what that peak would be if it was a coupled spectrum. So it's telling us how many protons are directly attached to that carbon. Okay, and of course that's the information that we lose when we do the decoupling. But we greatly simplify the spectrum, right? That top one is much gnarlier than the bottom one to try to interpret. All right? Okay, so yeah, we'll talk about some more kind of experimental details and how different ways we could do the decoupling, and then we'll do a little bit of that stuff. We'll talk about coupling, J values and things like that, and then chemical shifts and stuff like that. All right?
Very good.
Okay, so problem sets next Wednesday?
Yep.
Okay, good.